Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Welcome back. I think we're ready to start this afternoon session. I think this morning we had a great opportunity to frame a lot of the issues. This afternoon is going to be more free-form. We're going to explore some of the details of the front end, largely, what the voter sees and how the voter can participate in a verifiable process without, hopefully, it being too onerous on the voter so that it really is practical, and see some real instances of this. This is going to be started by Ron Rivest, who will talk about some work that has actually been fielded for Scantegrity in municipal election. Ron, I guess, is a sort of typical example of somebody who needs no introduction, but of course, when one says that, an introduction is then obligatory. So Ron is the R of RSA, which is used by everyone today when they use credit cards online and such. Has invented many systems, RC2, 4, 5, MD2, 4, and 5, I think 6, MD6, and many, many other things, not the least of which is the last few years he's focused some of his attention on voting systems, and we'll hear about how Scantegrity has gone now. So thanks, Ron.
Thanks, Josh. It's a pleasure to be here. It's great to have a voting workship here, so thanks to you and Cindy and all of you who helped put this together. I think it's great to get together and talk about voting, because it's an exciting area, and as Ben says, it's hard, and I think we're making progress on it. So I'd like to report today on some progress. What happens when a bunch of academics get out of the ivory tower and get their hands dirty and really try to help run an election with one of these systems. And it actually worked pretty well, so I'll tell you about that. So the goal here, do we have a screen, please? Do I need to do something? There we go, okay. The goal is to explain to you this particular system and explain to you what happened, at mostly good stuff, at the Tacoma Park election, November 3rd, this past November, where the mayor of Tacoma Park got elected with one of these systems and 6 city council members. This is a system with a whole lot of people involved. David Chaum is the lead and the main innovator on this, and I'm one of the participants in this. So, and the key idea of the interface, just to give you a heads up, I think this works on me. I think I just have to, there we go. Well, there's a little, there you go. So the key thing is when you mark the oval on your OpScan ballot, you see a confirmation code appear. So you see 631 appear there. And that's sort of the main innovation as far as the voter user interface appears. And that all gets wrapped in systems behind the scenes to make the counting verifiable and so on and so forth, as Ben said. But in some sense, that 631 is the encryption of your vote. So the end-to-end systems, or the truly verifiable systems, as Ben explained, are systems that typically involve a website where stuff gets posted, stuff that doesn't reveal exactly how you voted, but allow you to check that your vote was recorded correctly, and also allows anybody to check that the tally is correct. We don't want people selling their votes, so you can't post the votes in bare form unless we give up on privacy altogether. And some cryptography is used. Cryptography here tends to be less mathematical than the stuff that Ben talked about, as you'll see. I'd like to think of the verification as involving 3 parts. If you want to verify all the way from the voter's head to the other end where the tally is, you want to verify effectively 3 things. One, that the votes were cast as intended, and the voter can do that because she knows what she intends. That they're collected as cast, some kind of verifiable chain of custody, and that they're counted as collected. This is the tally that needs to be verified as well. And anybody can do the last 2, or the last 1 anyway, and the voter can check that collected is cast. Check that her vote is collected the way it was cast. So just voter verified paper trails only checks the first of these. You can see that your vote is correct on the paper, but after that you're depending on the election officials and so on. So the end-to-end systems provide this buzzword software independence, plus a verifiable chain of custody and a verifiable tally. So Ben gave a very nice overview of the general properties, and this is just a restatement of those. So Scantegrity, this is this second iteration of this. I'll just talk about the second version. The key philosophy here is you take a standard voting system that voters are familiar with, and you add a layer of mechanism that gives you this additional verification capability. So by and large, this all feels very familiar to the voters. They're taking the ballots, they're marking ovals. Things get dark when they mark the ovals, and by and large, it all works. In fact, one of our problems was it was too familiar. Voters didn't notice the differences in many cases. They just thought this was their traditional OpScan ballots, and the little numbers that appeared, who cares whatever they are, I don't know. So we didn't do enough education to the voters about the differences. So it feels very much like an optical scan system. The new things are, it's got a invisible ink for the confirmation code, so when you mark the ovals, you're using a special pen that has special ink in it, and when you mark the oval, the ballots are pre-printed in sort of reverse font here, so that you have a confirmation code of some sort that appears in the oval. So you can't mark outside of the ovals, in fact. The pens don't make any mark. You can't circle a candidate's name like you were talking about, Paul, or do things like that. So it's nice in that sense, and it gives a nice solid oval when you swipe them. And we had a pen with two tips on it. One was the chisel tip that you see here. It allows you to swipe the oval with one swipe and make a nice dark mark. And one was the fine tip at the other end, so you could turn it around if you want to do a write-in ballot. We had write-ins on this election as well. But the main point is that this is like an OpScan ballot. So if you're an election official that doesn't want to know anything about this new mechanism stuff, and you can just say, well, can I get all my traditional stuff? Yes, you can. You can do hand counts. We did a full hand count afterwards. You can do random sampling and auditing, whatever you like. You can treat these as ordinary OpScan ballots fully, and then the additional mechanisms will give you this verification capabilities that we talked about. So we had a connection with the city of Tacoma Park, which is a very progressive neighborhood north of Washington, D.C. We're looking for ways they have complicated elections. They've got IRV and things like that, so they needed some interesting technology to support that. And there was a connection with one of the team members, Rick Carback, with the election officials, and that grew into a relationship where we agreed to try a pilot. And this was, and we had a trial election in April, and then a mock election, and then the full real election this past November. So the main thing, as I said, with the interface is that the special pen marks the oval and then shows this confirmation code. So there's some special ink, there's some gallic acid and some other stuff in the inks that David Chaum can tell you about more. We've got an ink consultant. We're trying to reformulate the inks so they don't damage the print heads as much. We had problems printing the ballots actually a little bit. We had Epson inkjet printers. We took the cartridges and we filled up the cartridges with our inks instead of the standard inks, and that worked pretty well. But the cartridges, the print heads tended to die fairly quickly, and so we went through a few print heads like that. And I think with a new formulation that'll all be fixed. But these are the things you'll learn by really doing elections. So the confirmation codes are random. The voter can copy and take them home. Those are encryptions of her choices, if you like. I think it's the simplest way to look at it, given what Ben has said. So the confirmation codes can be viewed as encryption, and they're unique per ballot. So each ballot has an identifying number, and the combination of the ballot number and the confirmation code is an encryption of some candidate's name. Okay. The officials post the revealed confirmation codes, and the voters can look on the website after the election closes to see that the ballot, first of all, is recorded as having been scanned, and second of all, what the confirmation codes are that the voter should have seen. Now, what's the point of having these confirmation codes revealed like this? The point is that if the voters see something that's incorrect, they can protest. There's a protest protocol. So the voter says, you show this confirmation code instead of that confirmation code. Voters can be malicious here, and they can protest to discredit the election. And so you'd like to be able to distinguish between a protest where a voter is just being a troublemaker and a protest where the voter's got a legitimate complaint. You can tell here with a system like this that the voter's got a legitimate complaint because they know a confirmation code they shouldn't have been able to know without having actually marked the ballot. right? So that's the point of having the confirmation codes only revealed when you mark them. So the voter only sees confirmation codes that they actually voted for. The fact that they know the confirmation code is good evidence that they actually voted for them, and it should have been posted. Okay. And we had a lot of debate about how long the confirmation code should be: 3 digits, 2 digits, 4 digits, 6 digits. We ended up with 3-digit codes. Okay. Any questions about that? Sort of a key thing. Yes.
It seems like you run into a problem if someone ruins a ballot. They can't take another one because then they know a confirmation code didn't get counted and they can complain about it.
So spoiling ballots, the usual sort of procedures apply. You turn the ballot in, it's recorded as spoiled, and yeah. Okay. And there's also another part of the auditing procedure where we spoil ballots, so I'll tell that.
Yeah, maybe what wasn't clear was that probably the codes for one ballot is not going to be valid for another. So just because you weren't...
Oh, yeah, so that was the behind your question. I didn't understand that. The confirmation codes are unique, the random, and I should have said on that line, and unique per ballot too. So that, in fact, even unique across different races, so that the same confirmation code doesn't even appear on different races on the same ballot. Yeah. So there's the limits of my PowerPoint skills. We actually had, at one point we had a letter and a digit, and we switched to 3 digits because it seemed like it would be easier for voters to get used to. Okay, so here's the behind the scenes stuff. So you see the interface. So there's this website, there's this encryption process. The encryption really is a random encryption, if you will. The confirmation codes are random, so how do they get decoded, if you will? How do you verify that the decryption is being done properly, that the tally is right? So here's step one. This is what happens behind the scenes before the election starts. And I guess there's I'll explain. So there's a data structure created. This is the data structure. It's got a column here for the ballots. This is a ballot serial number, another ballot serial number. Within a ballot, there are various confirmation codes that might appear. In these slides, I'm using 2-letter combinations or letter-digit combinations. In the actual election, we had 3-digit combinations. So there's one column for these confirmation codes. So this corresponds to the ballots that were printed. Then we have some intermediate nodes that are just sort of random numbers. And then we have a final column which has one entry for every ballot entry. So if there's a Tom and a Dick on the ballot, there'll be a Tom and a Dick that correspond. And the correspondence is indirect and it goes through this data structure. So the first confirmation code on ballot 251 corresponds to Tom. And the second confirmation code on ballot 251 corresponds to Dick. And this is the correspondence. And these edges in the graph here are committed to ahead of time cryptographically by the election officials. So we have a cryptographic commitment procedure. If you don't know what that is, that's basically just an encryption. So you take the pair of things, which is the confirmation code and the ballot number, and together with this number, and you just encrypt them all together with a key that's unique to that encryption. And you can open it later. You're putting it in an envelope. A commitment has 2 protocols. One is committing to, which is encrypting, and the other is opening. You can open it later and say what was inside. And so we can see that this edge is there later on, but we're going to hide all this data structure. And we had a threshold encryption scheme set up. The election officials, we had 4 shares. There were 4 election officials on the Board of Elections. They each had to have a password to open their thing. We had a threshold of 2. One of them actually forgot their password, so we only had 3 active election officials, but 2 was all we needed anyway to make it work, and that worked fine. It was scary if we lost it. So this is the data structure. Any questions about this data structure? Okay. So then, before the election, this is all committed to. The pile of commitments is there, but the connections are no longer visible anymore. They have to be opened to reveal them. And the ballots are printed. And there's more to say about the printing process. I mean, that needs to be secret as well, right? Because the printer knows the correspondence here. So that these are underneath the invisible ink. You can't quite see them here, I guess, right now. We actually worried about people being able to tell what the confirmation codes are without having to reveal them. There's some chemicals or some special light you can shine on the ballots to see them. That seems to be pretty good against those kinds of attacks, but more research could be done there. Anyway, so this is the start of the election. So everything's posted on the web, all the commitments are posted, the ballots are printed, and we're off and running. Then the voters vote, the ballots are scanned. The scanner is a traditional Fujitsu desktop scanner, but it doesn't do OCR on the confirmation codes. It just looks where the ovals are marked. Those get translated into then positions on the ballots and posted. So the confirmation codes that should have been revealed are checkmarked and decrypted on the website. So on the website you can see ballot 251 should have revealed F7. And so the voter, when she looks up her ballot, can see that this is the confirmation code she should have seen. So the voter has after she goes home, she's written down on a separate piece of paper the confirmation code she saw. She took that home, and she's got her ballot number and the confirmation code. She looks that up. She says, yep, they have my confirmation number correct. They have recorded the confirmation number I saw. I'm happy with that. They've got essentially the encrypted value for my vote. They've got the F7. And voter who had 302 has her encrypted confirmation code posted correctly too. So at this stage, the voters have done their part. We've verified that it's vote as intended, so the voter knows that they marked the oval next to the candidate name that they liked, and the website is now posting the correct confirmation code. So the voter, we got the first two steps of verifiability done: vote as intended and collected, cast as intended and collected as cast. And now we want to do the tally. So this involves essentially a mixed-net kind of computation, like Ben talked about, a little bit different. So if you view this thing as a mixed-net, this graph structure maps this F7 to someplace over here. So the election officials who know the graph structure, or when they combine their thresholds, they recompute this graph structure, know what ought to be checked. If we take the path that goes from F7 to some candidate over here, whichever one it was, you can check every node along the path. So the election officials post those check marks. So there's some path that goes from F7 to one of these candidates, and I've checked every vertex along that path. And there's some path that goes from this check mark to some candidate over here, and I've checked every vertex along that path. Now we've got to be careful here. We don't want to tell the world how each particular voter voted. So we can't reveal these links so that the voter who had 251 can see that, yes, indeed, this is the path, this is the edge that corresponds to that, and that's the edge that corresponds to that. And because if you could trace those paths all the way across, anybody could sell their vote. You could see that F7 corresponds to Dick. Well, here in case this is the small sample issue that Ben talked about too. You know that everybody voted for Dick in this election, but there's only got 2 voters. But you know what I mean. So here, we want to confirm that these 2 check marks here correspond to the endpoints of these paths coming from these 2 check marks over here that go through these 2 check marks without revealing what the paths are. Right? So we want to have some path checking process that works without showing what the paths are. So every edge in this graph needs to be checked. Either both endpoints should be checked or not. So how do we do that without revealing the paths? So this is a process called randomized partial checking that Ari Jules and Marcus Jacobson and I worked on. And it works as follows. So we, I guess before we get to that, it's clear that once you've got the check marks around, you can do the tally so that you can see that Tom got no votes and Dick got 2 votes. So we know that that's the alleged tally for this election, assuming that the check marks are lined up properly, but we have to check that the check marks are lined up properly. So how do we do that? So we start off like this, and we go through the middle nodes one by one, and each middle node is the middle of a path, and if it's unchecked, it should connect on the left side to some unchecked node, and if it's on the right, it should also connect to some unchecked node, and if it's a checked node, it should connect to a checked mark on each side. And we're going to check for each node half of that, so we don't reveal the paths. So we can check the first node, and we actually use stock market prices on the day of the election to generate pseudo-random numbers. So we took the stock market of the Dow Jones Industrial Average and hashed that, which shot 256 or something, and got a bunch of random bits. So we had, and you can argue about whether that's the best thing to do or not, of course, but that's what we did. So we had a bunch of zeros and ones, and the first one was a 1. So this first node, we checked the right-hand side, and so that was the commitment here was open. So we can see now where this edge goes. It goes from this node over to Tom, and both of those are unchecked. This is unchecked, and that's unchecked, so that's cool, right? We don't know where it goes the other way. That's okay. So now this node, we also got a 1. We look this way, we see that it goes down to Dick, and that's checked, and this is checked, and we go down through all of these nodes. We're checking essentially half the edges in this graph, checking that either they have check marks on both ends or check marks on neither end. Okay? And the assertion then is that if somebody was trying to cheat this process and have these edges go in screwy ways or put the check marks down in a screwy way so that edges didn't have this property that they were always checked on both ends or checked on either end, then we'd have a pretty good chance of detecting problems. One edge was wrong, we've got a half a chance of, every edge has got a half a chance of being examined. So we'd have a good chance of detecting one. If there's more than one, there'd be an overwhelming chance that you'd check it. So this gives us confidence that the overall tally is correct. We see what's posted. These check marks are posted. These are opened up. These edges are opened up. We see where half of the edges go. We can check the check marks on both ends of the endpoints. And we can see that everything looks cool, that the check marks seem to be right. But we're not seeing how anybody voted. Right? We're getting high confidence that this process, that the tally is giving us the right answer without actually seeing how anybody voted. This F7 is checked. This could have been an error. Well, again, we have the small sample, but maybe I should have done it with a Tom and Dick switched or something. But you get the idea. Any questions about? All right. So that's the verification of the tally, right? So we have cast as intended. You can see that your ballot was marked as you intended. There's a step here. I need to talk about the printing of the ballots a little more, and I will. Collected as cast, so the voter can check that her ballots are posted, or confirmation codes are posted correctly, right? So the encrypted choices that she made make it properly to the website. And then counted as cast, that was the last thing I explained, was how the checking does of what's posted on the website. You can confirm the tally and see that everything was cool there. So let me talk a little bit about the ballot production printing, because that also needs checking, right? So there's an issue here. The ballots are different. They have confirmation codes on them. They have serial numbers on them. And the voter is trusting that when she marks a particular confirmation code, that it's associated with the correct candidate. And so you actually need to audit that as well, because if the printer were to switch the confirmation codes in a given ballot, you'd have problems, right? So, or switch the names of the candidates, because the voter doesn't see the paths going all the way through the data structure either, and can't check that the marks that she sees there's on her ballot going all the way to the end. So you need to check that the ballots are printed properly. And so we had Lily Coney from the Electronic Privacy Information Center randomly pick ballots during the day, mark all of the ovals, and then we would spoil that ballot, so it's marked officially as spoiled. And then on the website, we would open all of the commitments and see what went on. So for those ballots, so you could trace through all of the choices for that. So you could check that the data structure is entirely consistent with those ballots there. And we did that for about 50 ballots during the day. Okay, so enough to see if there's any kind of major issues happening there. So we did a ballot production check. The checkmark consistency check I talked about, public tally we talked about there. So that's really what you need to verify the correctness of the election outcome. We've got cast as intended, collected as cast, tallied is collected. Okay. Any questions on? Yes?
So a lot of elections in recent years have been decided by dividing voter intent. And in this system, given that there's a physical mark on paper, I'm wondering, in this election, did you run into any problems where an oval was kind of marked, or both of them were sort of marked?
These were scanned by Fujitsu scanners. We had, and so they were looking for just darkened ovals. We had, there were a few cases. We also had write-ins and things like that too. So that we could, I mean, the voter intent was more along the lines of somebody checked off a candidate and then also wrote their name in on the write-in line and checked the write-in box, oval too, sort of things about that, which is a little different. I mean,
People were saying that was a squiggle kind of close to the oval.
it's actually hard. One of the nice things about this is it's hard to do. You can't write outside the ovals, and you had the chisel tip for writing inside the ovals, and so it made a big broad swath. So there was very little of that, maybe one ballot or something like that where we had.
The follow-up question was, could this system work if electronically, where say 2 copies were printed with the codes, and then the voter had a chance to compare their receipt that they were going to take home with what the computer had printed, and then that's that. It's like a pure Boolean choice.
Yeah. Right, it'd be nice to get rid of analog things sometimes because we have a lot of issues there. But every piece of equipment you add to a system to make it more digital in some sense is a piece of system you've got to audit and check. For example, the recording of the confirmation codes here, we decided to do that have the voters do that by hand on a separate little piece of paper that they had a pad of in the voting booth, and rather than have it printed out, because then you have to verify that the printer was doing the right thing. Another complicated piece of equipment. So the answer to your question is, can you do X? The answer is probably yes, is a generic answer, but you have to see how many extra layers of mechanism you need to check those extra parts that you have. So you have to push to keep it simple. On the other hand, you want enough mechanism to verify all the way through. So some more comments. The ballot production is sensitive. You need to keep the PDF files that are secret that the printer is doing. So you're trusting the printing process. It's not a question of integrity here, it's a question of privacy. So the ballot printing needs to be private because they're unique ballots and you don't want to leak out which code numbers ended up on which ballots. We talked about the ballot production being audited, and what Lily Coney did. You can imagine another attack where you have to think of all the different ways somebody might attack a system like this, right? As David was going through, printing duplicate ballots, it's detectable if voters both got the same ballot and they both checked online, but they happen to vote differently, then one of them would protest. So things like this you need to think through. So we actually had a real election. It was great. This is the first U.S. governmental binding election for one of these end-to-end schemes. There have been a lot of others, as David talked about and Ben mentioned, where we've had organizations, but this is a governmental binding election. There's one poll site, 6 wards, 1,722 voters, just one poll site there, so it was a small jurisdiction. 66 voters verified online, which is enough to give some confidence that all that part's working well as well. I think a lot of voters, we did some post-election surveys, a lot of voters didn't actually realize that they could verify online until later. We had this mock election I told you, and they said, "What's the problem with this system? Because is it really going to work for voters?" And they decided the problem was me. Right? I'm serious here, right? They had me up in the front desk explaining how the system worked to voters as they came in, and that just took far too long, right? So that was about 8 minutes per voter. So here we got it down to 2 minutes per voter by cutting me out of the loop. But the consequence was that the voters didn't all understand what they were doing anymore, right? They didn't get this nice lecture ahead of time explained. So far too many of them didn't realize that they could verify online and stuff like that, even though we had signs up and explanations and things like that. So, yes?
You'd explain 8 minutes per voter would have taken you a week solid, day and night.
We were in groups and stuff like this.
How were the absentee votes handled?
So absentee votes, they were mailed out without the special pens. So the voters used ordinary pens there. We could have, but it's a great question, right? So does this system work with mail-in, right? You could mail them out with the special pens, and then everything's pretty much the same, except for the fact you don't have protection against coercion locally when the voter's voting, as you always have with mail-in. But the voter can then check online and everything. Yes?
Do you have some information that can be got from one of these, just sort of probabilistically? Like if the white part really comes out white when you scan it, can't you probe randomly, maybe learn some information about what the numbers are?
So this is the Ross Anderson chip and pin, or the pin attack, right? So you have various, there are attacks for banks, pins that are mailed out where people have taken pins and probed under the scratch soft surface to see where the font is there. So we actually jittered the positioning of the confirmation code. I mean, this is all sort of academics going overboard on some of this, but you can actually protect against some of those things. And so it's a real question as to whether the technology we've got for printing these in a way that's invisible really works against. It won't work eventually. I mean, you can always have some kind of attack. I guess we'll take a mass spectrometer and take micrograms of stuff out of the thing. So the question is how well does it work? So if there's some good chemists here that want to play with this, we'd be happy to. Josh?
Did the final verified tally perfectly match the upscan tally that came in?
I think we had the hand tally. I think we had a couple of cases where there was a voter intent issue. where the OpScan, the machine said it's illegal because they voted twice, but it was voting for the candidate and then writing in the same candidate's name on write-in. And I haven't talked much about write-in. We handled lots of interesting complications. I mean, you get into real elections, there's absentee ballots, early votes, so that people went early downtown to vote, and that was using the pens. Provisional votes, so you had to be able to handle voters who weren't clearly qualified at first and then later were. Spoiled ballots, so voters would make mistakes and need to come back and get another ballot, so you have to mark them as spoiled. Plus we had the ballot audits that were class of spoiled ballots. Privacy sleeves, David Chaum is fanatic about privacy and really cared that voters not be able to walk around with a bare ballot. They had to go in a folding black cardboard thing that then got stuck into the scanner, and the scanner sucked it out of that. So this was not something I'm used to in Massachusetts, but really protects your privacy while you're in the poll site from anybody seeing your thing. We had write-in ballots, and there was a special phase after the ballots were scanned to be able to interpret the write-in. So there's a program there that said this is a ballot with a write-in. There was a pixel image of the write-in field, and then somebody could type in what the interpretation of that was. And that gets posted too, and you can look and see what that is. IRV, so there's the instant runoff voting, which is not my favorite election system, but they wanted to use it there. So you mark first choice, second choice, third choice, and there's a process for figuring out who wins the election. External auditors, Ben was one of our external auditors. Ben did a fantastic job at writing code, or understanding all of the entire system, writing code and himself that looked at everything on the website and checked that it all made sense. And you can look at his website and see the auditing process. So it's all public there. It's on the website, so anybody can look at it and do these checks. And Ben was one of the official auditors. Phil Zagorski also did similar checks. We had 2 scanners for higher throughput. There was Spanish and English printed on the ballots, et cetera, et cetera. This is David Chaum with the ballot box. So these are big sort of laundry bins that we bought for the ballot boxes. That's a ballot box. There's the other one. This is a desktop Fujitsu scanner hidden in here. This is a custom little piece of mechanism that David got engineered for the thing. You slide the ballot in here with the privacy sleeve on it. It falls down here. There's a little button that keeps the privacy sleeve from sliding all the way into the scanner. The ballot goes all the way into the scanner and falls into the box. And here's a laptop in this box here that does the recording. There's a seal of the city of Tacoma Park and a locked ballot box, whatever. So that was. This is the ballot itself. So we had, you can see the, one thing that wasn't so great was the font on these. The font didn't have as high a resolution as you'd like. The one complaint we had that seemed like it might be sort of legit or whatever, understandable, was somebody couldn't tell a 0 from an 8. So there was like only 1 pixel different there, and that needs a little improvement. But I think it's all doable. So somebody's marking first choice, second choice, third choice, and if you mark your third choice, you can do a write-in. These are alignment marks for the scanner. This is the barcode for the serial number as well. This is the human readable version of the serial number for the ballot. Instructions in English, instructions in Spanish. So you can see this was also, the yellow regions are the ones that are sensitive to the special links. So the write-in area, you could write in. You couldn't write outside of that area or the ovals, though. Some of the issues, ballot printing was challenging, as I mentioned. I think the inks we had were not friendly to the print heads. A lot of the voters didn't quite understand they could verify online. Long-haired professors talking too much. I take responsibility. That was the mock election, though. No special pens for absentee voters, so the absentee voters could not check online, other than the fact that their ballot was, they couldn't see the confirmation codes, right? So they just filled it in with the ordinary, and so they could see that there was confirmation codes posted. They were treated like that because the posting of the confirmation codes on the website didn't depend on doing OCR in the ballots. It was just looking for where the ovals were dark and then translating them back. And then, but I think if you wanted to do it, mail it in Washington, you could just mail everybody a pen, I guess, or something like that, right? So, I think we're not as good as we could be on if somebody marked the ballots post-casting, right? If somebody didn't fill in a ballot at all, just wanted to cast a blank ballot or left a race blank and somebody filled it in later, the voter doesn't have a credible way of protesting that. because they don't have a confirmation code that says I didn't vote for anybody. So if you had a none of the above choice, maybe that would take care of that. A large team. David Chown was the lead. Rick Carback was the graduate student from the University of Maryland that had the first contact with Tacoma Park. Jeremy Clark, John Conway, these are graduate students. Stefan's now at NIST working on voting. Peter Ryan is the inventor of the Prêt à Voter. Alan Sherman's at University of Maryland. Pori Vorva is worked really hard from the George Washington University at making this all hang together. The Tacoma Park officials, there's a board of election. We had, as I said, a four-way team that had threshold crypto. So these are the four election officials that the board of elections folks that actually worked with us directly and managed some of they took a special role in the managing of the crypto keys. And as I said, Ben did a great job with the auditing of the information that was posted on the website. Lily Coney did the ballot audits. Phil Zagorski also looked at the information that was posted and did checking on that, and Lynn Baumeister did some of the surveys that we have too. We got a separate paper coming out on some of the survey data from this. So that's basically what I wanted to say. The end-to-end systems, it really worked. I mean, the election worked. The voters seemed satisfied with it. I mean, I think there's some minor glitches here and there, but this extra layer of mechanism didn't seem to cause any undue problems. I mean, people who could check seemed to like it. And a lot of people didn't get the information that they could check soon enough, so they'd already cast their vote and they said, "Oh, I can check online," and it was too late to get their confirmation codes. But I think this is a very promising election. It says that these kinds of end-to-end verifiable elections really can work in the field in practice. You can provide this level of integrity guarantees on ordinary political elections. I mean, the scalability of the system, the business aspects of all this are, sort of not there yet. I mean, you have to make the printing work better and have a business organization this is just a bunch of academics sort of working with Tacoma Park, but I think there should be some process for making this work. And one point I didn't say is I think that, and Ben didn't say either, I think that you should understand that there's a bit of a trade-off here between privacy and integrity. Right? These systems are improving integrity because you've got an additional layer of mechanism, but there's an additional risk to privacy because you've got crypto keys, which if they got disclosed, could reveal how people voted. So if you had a state constitution that said, you absolutely have to have indistinguishable ballots and total voter privacy or something like this, the system doesn't have that because we're introducing a risk to privacy here. But with threshold encryption and stuff like that, I think it's a very reasonable trade-off myself. So that's all I wanted to say.
Thank you.
Happy to take questions.
Are there any further questions on the actual Tacoma Park process or Scantegrity process and how it works and what's going on before we get into sort of the open issues?
Did you have any challenges because people wrote their numbers down wrong? They wrote down an 8 instead of a 0.
Well, this one fellow that wrote down the 8-0 thing, presumably he agreed that he probably wrote it down. He said he wasn't sure at the time what it was, and he wrote down a 0, and the website said an 8. That was the only challenge we had. Yeah. So everything else seemed to work. Yes?
From an operational level, what do you think the increased cost per ballot is to use the inks and the pens and that sort of thing, right?
So it's not much. I mean, I think compared to having DREs, I mean, the nice thing about AppScan and paper-based ballot systems is the per voter cost is just the cost of printing the ballot. Here the ballots need to be unique, but that's not a big deal. The inks, I mean, this is graduate student time and stuff like this. And we had students filling up the ink cartridges, syringes, and stuff like that. So it's hard to measure exactly what that is. If you're doing it in a commercial operation, this technology would have to be refined and get real cost estimates.
There's no real expensive component to the ink or something. It's not like it's like a bag.
The ink is cheap. The printing has got to be unique, and that's different there. You have to make sure the ink works on those printers. You've got a website to run. That's about it. Yeah.
Do they want you back?
Pardon?
Do they want you back for the next election?
They do, actually.
Great.
So I'm not sure how we're going to do that.
Right, well, that's
Or if we're going to do that, but they do want us back, yeah.
Okay, so I want to sort of hit process a little bit here. We agreed beforehand that we wanted to try to focus on open issues and questions and things that improved. So In the spirit here of you're most critical of those you love, in some sense, I really do like Scantegrity a lot. I proposed, I came up with a list of about a half dozen things that seem to me are open issues that can stand improvement, and hopefully we can get other things going. So let me, maybe the best thing to do is just read it at this point. So the first thing that I find difficult is something that you came up with, explaining the system. The conceptual complexity, I actually find this more difficult than explaining sort of encrypt and, as Ben described this morning, the process of encrypt, and then we go through a mixnet or homomorphic encryption or whatnot to decrypt, because it's not quite encryption, even though it's mathematically simpler. The plugboard graph, I haven't found a good way to explain to people yet. I don't know if there is a good metaphor.
Yep, I agree. I think as we experiment with different systems and as we experiment with our explanations of these systems, they'll get better. But you're adding new mechanism. It's got a certain level of complexity to it. Somebody wants to understand what's going on, has to digest a somewhat complicated explanation, and maybe there's better systems to choose for that reason, or better ways of explaining this system. Yeah.
Let's see. Next on my list is the issue of the linkage between the verified and the traditional tally, which seem pretty close here, but I'm always concerned about a system where, well, we've got these two tallies and they're not exactly the same, and how do we reconcile them? So I like the linkage to be as tight as possible. And I'm always
the reconciliation between the
OpScan tally and the verified tally.
It was very close.
It was very close.
Yeah, very, very close.
Yeah, which is very good.
And all of them were explained by, there were some absentee ballots, there were some voter intent things, and they were all accounted for in the end.
Okay,
yeah.
good.
And
The process was very comfortable for the election officials, I think, in terms of understanding that there were some, and there's always discrepancies, and you have to go through and try to figure out what's going on, and here you had good solid records of that, but there were no really new categories of issues introduced, I think.
A third thing on my list was issues with a corrupt or a malicious printer who knows the codes. Somebody has to print it, some machine has to print the codes. If you do know the codes, you could create spurious challenges or conspiracy.
That's right. That's right. And if you know somebody knows the codes ahead of time, that's exactly what they could do. They could challenge and seem credible for that. You can always go back and look at the ballots too. So if somebody says I voted for X and you're showing Y or whatever, these ballots have serial numbers. You can go back in the back room and pull out that ballot and look at it. There's also been some work that Alex Essex and others have looked at for trying to separate the printing out. So you could have printing in stages and have different layers of printing going on and stuff like this, where the inks mix in a different layer somehow. So maybe the serial number goes on at one, or I don't know if I understand these proposals very well yet, but there is a single point of failure there with this design, which is at the printing stage, and it's a failure if it fails for voter privacy or for the ability to protest.
Ron, actually, pushing on what you were just saying, the printing in layers, is there any, it seems like combining David Schaum's visual crypto with potentially some inks that can become active only when both have been printed.
Yes, there's room for research here and figuring out ways of mitigating this. I don't know.
Really interesting, because it does seem like that's like the one thing that's a little bit, probably the weakest point. If it can be resolved, that's even better.
I'll add a fourth and I'll stop there. We can do things later. But the fourth thing I'll mention is full voter verifiability, in the sense that I trust Willie Cummings, but maybe there's somebody out there who doesn't. As an individual, very suspicious voter, how do I have assurance in the integrity of the ballots? Am I allowed to spoil a bunch of ballots myself? Is there another process?
So that was a design decision. This is the first time this had rolled out. We wanted to try to keep things simple for the voters, and the best, purest solution to this is to have voters get a choice of ballots and spoil one and cast the other, something like that, right? So we thought about that, But throughput was an issue, getting the voters through, and complexity for the voters. They had to understand that they had this option. Asking the voters to randomly do something seemed, randomly pick a ballot, randomly pick 2 ballots, randomly pick one of them to cast and one to think. The election officials decided they didn't want to get into that, so we had a process where we had, designated representative to act as essentially a proxy for the voters to check on the ballots. But there's nothing in principle for why that couldn't have been done, or even on an ad hoc basis somehow. And as people, if this system continues to be used, as people got familiar with it, I could easily imagine sliding into that on a discretionary basis for some of the voters or all the voters if they wanted to. Yeah, there's no reason you can't. It's just sort of managing voter understanding of what's going on. For those that don't care about this, but many of them don't care about verifying this aspect of it.
Are there any other issues?
Let's see, this is going to be a little long. I first start by saying that it falls into what the remark you made at the end about there's always this little compromise on the privacy side when you do these things, right? But the example that you gave of keys being revealed, that really requires all or most of the election officials to participate in that. And I guess I've always been of the opinion that if you've gotten to that point, you've got bigger problems than running elections,
Yeah.
So that one is a little less of a concern to me. But in this situation, as I understand it, you have some opportunity for insider coercion attack, right? I mean, if there's still access to the ballots for the purpose of recount after the fact, right? And the coercer can force the voter to reveal his codes before, he can go through and look for a ballot that happens to have that particular...
The paper ballots are by state law kept for, or federal law, whatever, kept for 22 months. It's federal law, right? Isn't that?
This is for federal elections, yes.
For federal elections, yeah. So I'm not sure what the law was here, actually. But the paper ballots are identifiable, and a voter could be coerced conceivably because an election official said, I have access to the ballots.
And in fact, I mean,
now, in principle, the voter has a some choice about which ballot they get. So there's no table linking voter names to ballot numbers, right? So
that's not important if you can give them the sequence of codes that you revealed when you voted, right? So
they're all posted on the web, so that as soon as the election's over, the ballot anybody can knows those numbers, right? So as soon as the election closes, then.
But if I on my way out, before it ever gets posted, right? If on my way out, I reveal to a coercer, or I'm asked to reveal to a coercer what my sequence of choices were, right? That's going to eventually link me back to a particular ballot, paper ballot in the counting process, right?
Yes.
Okay.
Yep.
And
that's correct.
And I guess the reason I bring this up is, I'm aware of certain real-world coercion attacks, and most of them from the city of Albany, and all of them that I'm aware of involve these.
Albany, New York.
Somebody on the inside. What's that?
Talking about Albany, New York.
Yeah.
I grew up in Schenectady.
So I mean, I think we need to be careful. I guess what I'm getting at, and just summing this all up, is I think that it's safe to say that we're building our assumptions of privacy on the assumption that not all election officials are simultaneously corruptible, right? But to build your assumption of privacy on the notion that no one will ever be corruptible is a slightly weaker assumption.
Yeah, I think that's a fair comment. Yeah. The fact that these ballots exist, they have serial numbers on them, and are uniquely, you can go back and look at them, increases the risk to privacy and coercion attacks. I agree.
Anything further? Okay, well, thank you again, Ron.
Sure.